Hello, my name is Dennis Strown. Thanks for coming to the talk on big players, emotion in Twitter communities tweeting about global warming. So the background for this project is looking at two lines of research on climate change. One deals with the relation between a person's concern for the environment and factors like their level of education, life experiences, while the other is looking at how sentiment and emotion can actually be influencing factors as far as a person's perception of risk and their support or lack of support for a given climate policy. So we're looking at putting Twitter into this as a source of public opinion that's available for research and is laden with emotion, in this case, emotion about climate change. So we're focusing here on what we're calling the big players, which we define as a subset of users that are demonstrating a very, very high level of activity on Twitter. We want to know, are these players representative of the general community that's talking, in this case, about the hashtag global warming? And more specifically, can they predict the emotion levels in the general community? So we're using a Twitter data set we've collected. It has over 400,000 tweets with hashtag global warming. These are coming from nearly 240,000 Twitter users, and it's spanning 20 months. So we've got the first tweet coming out in January 2018, all the way through the end of August 2019. Now, natural language processing is challenging anyway, and on social media, it can be especially difficult. The users are not professional authors. They're not clearly organizing their thoughts. It's more of a stream of consciousness. It's full of grammar mistakes, errors in punctuation, spelling mistakes that are not always mistakes on purpose. Sometimes people want to say, I'm scared of global warming, or whatever it is. There's non-standard capitalization. There's atypical abbreviations. We have non-traditional elements like emoticons, high levels of noise from things like spam and off-topic tweets. This brings us on Twitter specifically. The texts are very, very short. It's now 280 characters, used to be a limit of 140. This kind of creates a lack of contents, which can make it hard for the NLP algorithm. And there's a lot of retweeted text, of course, in the form of retweets. So if we look at our sample tweet here on the bottom, we see a lot of emoticons, the infamous OMG, 3 exclamation points, a lot of words that should probably not be capitalized. I should be capitalized. And then the author says it's hit as hell, probably means hot as hell. So we have an idea of what we're dealing with here. We're using the Weka machine learning platform, which I believe is fairly well known. On top of that, we have the Effective Tweets plugin, which is basically gives you a lot of tools for NLP dealing exactly with Twitter. The tokenizer is expecting tweet text, and we'll separate that into the different elements, words, and so forth. There's options for standardizing websites and usernames. You can add stop lists and stemming. We did a good part of this using the Porter stemmer and the stop word list from Lucene. We were not getting consistently better results. So what we're presenting here does not actually include those, but they're available. And there are many lexica for both sentiment in terms of positive, negative polarity and emotion, which is what we're interested in here. So the one we're presenting is the lexicon, the affect intensity lexicon from the National Research Council Canada, NRC. So this is providing a lexicon for 4 out of the 8 base emotions, according to Plutchik. We can look and see in that ring with the magnifying glasses, we have the 8, and the ones we're actually using with our lexicon are under the magnifying glasses, so anger, fear, and sadness. Joy, which may not seem quite as pertinent to climate change conversations, but it is the pair of sadness, so it makes sense to have it in there. So we looked at the sample tweet. We can actually bring it through a filter on the plugin for Weka, and we get out an emotion vector, which is a sum of the emotion levels for all the words in the tweet, according to the lexicon for anger, fear, sadness, and joy. And we'll see that again in a little bit. So we talked about the big players being very, very active, and we've defined the 4 types of activity, which we call communication categories. So on the bottom left there, we have original tweeters, retweeters, retweeted authors, and mentioned authors. And although it's probably fairly self-explanatory, an example always helps. So if we have 2 Twitter users, Alice and Bob, Alice does an original tweet. The media viciously attacked @RealDonaldTrump for skipping the hashtag G20. So we put her in, she gets credit in the odor category, which is the code for original tweeters. These codes we see down the middle there, both in the, they're used as the attributes that we'll see on another slide, and they're in the program itself, which is making all of this happen. So a little bit later, Bob retweets, and that's the standard syntax for a retweet on Twitter, that same tweet from Alice, so he's credited in the retweeters category. But at the same time, we credit Alice as a retweeted author since Bob retweeted her. And even though real Donald Trump did not actively take part in this tweet sequence, he gets credited twice, once for each tweet, with being a mentioned author. So the big players, is it the top 5, the top 10? We actually look at a range of them from 5 to 25. And the big players will be that many, the top that many in whichever of the 4 communication categories we're looking at. So the idea behind this top N is we'd like N to be reasonably small. So someone using this method in another study, maybe on climate change, maybe on something else, who wants to identify a set of users who are ideally representative of, to some extent, of the general community, we'd like that to be a small number so that they can go look up profiles or follow tweet chains as necessary without it being a massive undertaking. So we have 4 categories of big players. The regular players are basically everyone else who did an original tweet within the time period we're looking at that are not, of course, in any of the big player categories. Fairly simple. So at the bottom, we have an example regression model. On the left, we have the dependent attribute. This will always be the regular players. We're always trying to predict what they are doing in their original tweets, which is why we have that odor code there. And then there's actually, there'll be 4 models, so 1 for each emotion. On the right side, we have the independent attributes, and there will be 16 of them. So they're always big, the 4 communication categories and the 4 emotions. So 4 by 4, 16. Of course, down the middle are the coefficients and the intercept. So to get one of those models, we have to do some processing on the data. Our database is full of tweets that we've brought in from the Twitter Developer API. We store them in the JSON format that we get them from Twitter. So we basically pull those for the period we're looking at, which we call a tracking run, and we run it through that filter on the Weka Effective Tweets plugin using the effective intensity Lexicon. That gives us a series of those emotion vectors we saw on a previous slide. At that point, we're going around the line here coming up from the yellow to the purple. We attribute all of those emotion vectors to the users, the authors that tweeted them or that they were tweeted about. And we're running daily averages. So all of the tweets in a given day will come into one set of running averages. And we also keep tweet counts for the users in each of the 4 categories. That makes when we run down to the green step, that's a bit easier because we just take the top N. And again, we do runs from 5 to 25 for the top, for the big players. So once we have the top N big players, whichever value N is taking at the time, we come up to the blue and we are regrouping those. So we take, as you might expect, the 4 groups of big players plus 1 additional group, which is all the regular players. And then we reduce those daily averages for those players by group and by days into week-long. So at the end of this blue period, we basically have, if you're looking kind of tabular, each instance is a week worth of raw emotion levels for the tweets for the regular players and the 4 big players. Again, already in the form of dependent attribute and 16 independent attributes. So that's not quite what we want, it's almost. We come down to this red for the last step, and what we're trying to predict really is the variation in emotion from week to week. So we lose a week here, but we take that same data set and basically subtract from each week the week that preceded it. And that's what we're using as our final instance set. And from that we create, if you're familiar with Weka, you know the ARFF file format. Basically 4 of them for each emotion, for each of the N levels of top N. And if you're not familiar with Weka, you can kind of think it's equivalent to a CSV file. So I've mentioned the word tracking run several times, and I don't know how well I explained it, so we're going to do that on this slide. Basically, we have 20 months of data, but we're only looking at 12 months at a time. And we are sweeping that 12-month period across all 20 months. So that's going to actually be 9 tracking runs to get through our full set of data. Now, for a given tracking run, we look at what we are, what's happening during the first 9 months. That's using to train the date, used to train the model. And the last 3 months we are using to test the model. So in effect, it's the 75-25 training test split is also giving us the idea of using what happened during the first part of the period to test what happened at the last part of the period, and to test the emotion levels going on in the last part of the period. So that's an interesting way of looking at this, but we also thought it'd be interesting to test what's going on predictive-wise during the period itself, kind of generally within the period. And so to do this, we did an evaluation configuration for with using tenfold cross-validation over the full 12 months. So here we're basically predicting within the period. And this is standard in machine learning. However, it's not quite parallel with what we were doing before. So we did a third configuration where instead of taking the last 3 months, we take the equivalent amount of data, but randomly taking random weeks throughout the whole 12 months. That gives us our 25% independent test set. And then we train on the remaining 75, which is also scattered through the 12 months. And that's our third configuration. Now, when we give the results, I'm actually only gonna go over 1 and 2, and the paper does as well, because the 2 predicting during the period configurations gave very, very similar results. So we will look at number 1 and number 2. For the tracking run, again, that we have that same picture, 20 months, I've started the slide here just to kind of give you the idea of what's going on as we take those 9 tracking runs. We ran several learners. We started with linear regression. It gives you a nice base for what to expect. It did fairly well, as we'll see. We didn't really have any reason to expect that this would be a linear relation between what the big players are tweeting and what we see in the regular players. So we tried several other learners, and there were none of them that did consistently better than linear regression. So both in the paper and for this presentation, we're presenting the results of linear regression. So here we have results for anger, and the top and the bottom correspond to that first and second configuration for evaluation. So the top is actually predicting within the last 3 months based on training during the first 9 months, and then the tenfold cross-validation is predicting throughout the period. So we have, in the last 3 months version, we have a PCC, Pearson correlation coefficient. The best one is nearly 0.4 at n equals 17. So if we, of course, if we had 1, that would be a perfect correlation. But if you're not familiar with PCC, we want it as high as possible, basically. And we see that as we get increasing values of n, it starts to fall off. And for very low values of n, it doesn't do so well either. That's going to be important, given the idea that we're looking for a value of n that will allow researchers to minimize the work if they have to go look at users. It looks like it's a little better when we're going throughout the period, but we did a series of reference runs to kind of anchor what we've done in, so it's not just one period floating off. So we basically, for this dotted line, what we've done here is, instead of getting the big players, we select randomly a set of players out of the general population that have enough activity that they will actually give us data to train on, but are not in the big player set. So you might think of them kind of as random medium players. So we see for the last 3 months, we're actually doing significantly better than what we get by just predicting random players. However, that's not so clear when we're doing it using tenfold cross-validation across the entire 12-month period. And again, for each of these lines, that's an average of 9 runs on the red line, and it's actually an average of 180 lines on the dotted line, because not only do we have the 9 tracking runs, but for each one we did the random pick 20 times, so we wouldn't get a lucky pick or an unlucky pick. It would average out. So these two things, when we see them for fear, it's even more apparent. Here we have the best n, which didn't do quite as well as anger, but we're getting a 0.3 here for n equals 16, which is 1 less than what we got for anger. But we see that very, very rapidly it falls off. We do not get good predictive capability for high values of n or for low values of n. We do see it for that range well above the reference line. However, the second thing that we saw that it looks like it's more of a straight good predictive capability for during the period. We see that it's not significant at all compared to what we can do just picking some random users out of the set. So how might we interpret this? We have kind of three hypotheses to present to you. The first is that the emotion being expressed by the big players is indeed representative of the larger community. And that was kind of our main focus with this. A second is that the big player tweets are actually influencing the members of the general community. And this is very interesting and perhaps merits some further research, but we got to remember, these are not causal models. We cannot say that. We have a correlation, which does not mean that we found the cause by any means. But it is interesting to consider. And also there's a third possibility that the big players in the community are actually influencing each other's emotional state. So each of these is worth considering. I've not shown you sadness and joy, not only because I'm limited on time, but also these models did not show a significant correlation. For joy, that's not necessarily surprising. We believe there's a fair amount of irony and sarcasm in the tweets on global warming, and that can make detection of that emotion very, very difficult. We did look at a number of individual tweets, and we did see a good amount of sarcasm there. So this is a very good hypothesis. So kind of in closing here, looking at climate change research, we feel we have important contribution here, because in psychology and in sociology, there are a number of studies that are looking at anger and fear with regard to framing messages, for giving information on climate change, or promoting advocacy or certain policy. So being able to use Twitter as a source to kind of fine tune the theories coming out of that research is a very important contribution. Unfortunately, we don't have something to offer for sadness, because sadness is also an emotion that's under kind of scrutiny in research on climate change. But we do have anger and fear, so we offer that. We have to, all the time, though, keep in mind that emotion is a very, very, very complex part of human cognition, which is also very, very complex in and of itself. So this is not necessarily a matter of just tweaking, get a little more emotion, a little less fear, or vice versa, to get your perfect recipe for whatever message you're giving. So we can learn from these models, but we have to be careful not to oversimplify what we're doing. So thank you very much. If you have any questions, I will be available at the question and answer session, and there's also my address, email address down at the bottom there. On behalf of myself and Roger Villemaire and Serge Robert, who worked with me on this project, I hope you enjoyed our talk and enjoy the rest of your conference. Thank you very much.